This number is wrong, or rather, almost everyone explains it wrong. 93 billion light-years wide. That's the figure you've seen in headlines, in documentaries, in half the space channels on this platform. But the universe is only 13.8 billion years old. Light travels at, well, the speed of light. So how does light from a 13.8 billion-year-old universe span 93 billion light-years? That gap looks like a contradiction. It has fueled 1,000 comment section arguments. It is not a contradiction. It is a clue about how space itself behaves. And once you understand why the number works, you'll understand something most explainers skip entirely: where this measurement actually stops being a measurement. So let's start with the myth everyone repeats. The myth goes like this. The universe is 13.8 billion years old, so its radius must be 13.8 billion light-years. Simple, clean, wrong. That assumption treats space like a fixed stage, with light as the only thing moving across it. For most of human history, that was a reasonable assumption. Space was the backdrop. Objects moved through it. Then, in 1929, Edwin Hubble pointed a telescope at distant galaxies and found something that broke the stage metaphor completely. Nearly every galaxy he measured was moving away from us, not just moving away. The farther a galaxy was, the faster it was receding. That relationship has a name now, Hubble's law, and it pointed to a conclusion nobody had proven before. Space itself is stretching. Not galaxies flying through empty space like debris from an explosion. The space between them is expanding. This single distinction is where the 93 billion number actually comes from, and it's the part most videos rush past. Picture two dots drawn on a balloon. As you inflate it, the dots move apart. Neither dot moved across the balloon's surface. The surface itself grew between them. That is a crude model, and cosmologists will tell you it breaks down eventually, but it fixes the intuition. The universe doesn't have galaxies moving through fixed space. It has space itself growing, carrying galaxies along with it. So when a photon leaves a distant galaxy 13 billion years ago and heads toward us, it isn't just crossing a fixed distance. The space it's crossing is stretching the entire time it travels. By the time that light reaches your telescope, the galaxy that emitted it is no longer where it was. It's much farther away now. That's the key. 13.8 billion years is how long the light took to travel. It is not how far away the source currently sits. Those are two different numbers, describing two different things. Confusing them is the entire source of the myth. And once astronomers account for that stretching, the math changes completely. The most distant light we can detect left its source around 13.8 billion years ago. But accounting for cosmic expansion, the object that emitted it is now calculated to be about 46.5 billion light-years away. Double that radius for the full diameter and you land close to 93 billion light-years. That's where the number comes from, not the age of the universe. The current distance to the edge of what we can, in principle, detect. So, no contradiction, just a distinction almost nobody explains clearly. Now the harder question, how do we actually measure any of this? You can't run a tape measure to a galaxy. Every distance in cosmology is inferred, built from indirect evidence, stacked carefully on top of itself. The first tool is redshift. When an object moves away from you, its light stretches toward longer wavelengths, shifting toward red. It's the same effect as a siren dropping in pitch as it passes. Astronomers measure that shift in the light from distant galaxies with extraordinary precision. The more the light has redshifted, the faster the source was receding, and the farther away, and further back in time, it is. Redshift alone gives you a velocity. To turn that into an actual distance, you need a second ingredient, the expansion rate of the universe. That rate has a name too, the Hubble constant. It tells you how fast space is stretching at any given distance, measured in kilometers per second per megaparsec. Feed redshift and the expansion rate into the equations of general relativity, and you can calculate how far a galaxy's light has traveled and how far the galaxy sits today. But there's a problem. Different methods of measuring the Hubble constant give slightly different answers. Cosmologists call this the Hubble tension, and it's real, it's unresolved, and most explainer videos never mention it. One method measures pulsing stars and supernovae in the nearby universe. Another reads the afterglow of the Big Bang itself. They disagree by about 9%. That's not a rounding error. It may be pointing at physics we don't understand yet. Keep that in mind. We'll come back to it, because it matters for how confident we should really be in any single number. For now, let's talk about the second pillar of this measurement, the cosmic microwave background. This is the oldest light in existence. Radiation released about 380,000 years after the Big Bang, when the universe first became transparent. Before that point, the universe was an opaque plasma. Light couldn't travel freely. It just scattered endlessly off free electrons. Then the universe cooled enough for atoms to form. Suddenly, light could travel in straight lines. That first light is still arriving. It's the cosmic microwave background. We can detect it in every direction we look at nearly uniform temperature. That uniformity is itself a discovery worth pausing on. The tiny temperature variations in that background, fractions of a degree, encode the seeds of every galaxy that would ever form. And critically, they also encode the geometry of space itself. By measuring the apparent size of those fluctuation patches, missions like WMAP and Planck let physicists calculate how flat the universe actually is. The result, to remarkable precision, is flat, not curved like a sphere, not saddle-shaped, flat. That flatness matters enormously for this whole calculation because it lets cosmologists use straightforward geometry to convert redshift and expansion rate into an actual distance. If the universe were curved, the same data would produce a different answer entirely. So the 93 billion light-year figure rests on three things working together: redshift measurements, the expansion rate, and a flat cosmic geometry confirmed by the CMB. Change any one input and the number shifts. That's not a flaw. That's what an honest measurement looks like. Now here's where most videos on this topic stop. We're not going to stop here, because 93 billion light-years isn't the size of the universe. It's the size of the observable universe. That distinction is not pedantic. It changes the entire meaning of the number. The observable universe is a sphere centered on us, defined by the farthest light that has had time to reach Earth since the Big Bang. It is not a special place in space. It's a boundary defined entirely by us, the observer. A civilization on a planet 4 billion light-years away would have its own observable universe, overlapping ours, but not identical to it. Neither sphere is more real than the other. Neither marks an edge to anything. So what's beyond 93 billion light-years? Almost certainly more universe. Just like this. More galaxies, more stars, more of the same physics playing out, forever beyond our reach. We will never see it. Not because our telescopes aren't good enough, because the light from beyond that boundary hasn't had time to arrive yet, and never will. Expansion means some of that light is now receding from us faster than light itself travels. That doesn't break relativity. Nothing is moving through space faster than light. Space itself is doing the moving. It's a strange loophole. Relativity limits motion through space. It says nothing about the space in between. So this is the honest shape of what we know. We can measure the observable universe with real precision. We cannot measure the whole universe. We don't know if it's finite or infinite. We may never know. That flatness we mentioned earlier, the flat geometry measured by the CMB, is consistent with an infinite universe. But it's also consistent with a universe that's simply far larger than what we can observe, curving so gently we can't detect it. Our instruments can't currently tell the difference between the two. That is not a failure of imagination. It's a genuine limit of what light can tell us. Some cosmologists have proposed the universe might loop back on itself, like the surface of a very large sphere in higher dimensions. If that were true, light could theoretically circle all the way around and reach us from the opposite direction, showing us the same galaxy twice. Searches for that repeating pattern in the CMB have so far found nothing. That doesn't rule the idea out. It just hasn't been confirmed. This is the part of science that headlines tend to skip, not the confident answer, the honest edge of the answer. 93 billion light-years is real. It's not a guess, not a rounding trick, not a headline exaggeration. It's the product of decades of careful measurement, but it describes a boundary drawn by us from where we stand, using light that has had time to arrive. Beyond that boundary, the universe almost certainly continues. How far, in what shape, whether it ends at all, Nobody actually knows. And maybe that's the more interesting fact than the number itself. We measured the edge of what light can show us. We have not measured the edge of what exists. If you want the next mystery explained with the same honesty, the rest of this channel is built exactly for that. Subscribe and we'll keep going. So let's push past the tidy number. 93 billion light-years is a radius built on assumptions about expansion that we treat as settled. They are not. The figure depends on a model called lambda CDM, dark energy, dark matter, ordinary matter, mixed in specific ratios. Change the ratios even slightly, and the size of the observable universe changes with them. The number is a prediction, not a tape measure. And right now, the model has a crack in it. Astronomers call it the Hubble tension. Two separate methods for measuring how fast the universe expands give two different answers. Not close. Persistently, stubbornly different. One method starts nearby, timing the pulse of variable stars and the light of exploding ones. The other reads the afterglow of the Big Bang itself. Both methods are careful. Both have been checked and rechecked by rival teams for over a decade, and they still disagree. That gap is not a rounding error. It may be a sign that something in the model is missing. If the expansion rate itself is uncertain, then the 93 billion figure inherits that uncertainty. Quietly, without most headlines mentioning it. This is the part the documentaries skip. The number sounds absolute. The physics underneath it is still being argued over at conferences. There's a second assumption buried in that radius too, that space is flat. Not curved back on itself, not closed like a sphere. Every measurement we have says flat to within a fraction of a percent, but a fraction of a percent multiplied across billions of light years is not nothing. If space has even the slightest curve we haven't detected, the whole shape of how big is everything changes, not the observable part, the actual part. This is where honest scientists stop and shrug, not because they haven't looked, because looking harder hasn't settled it. So what do you do with a universe that might be bigger than the number says, or shaped differently than the model assumes? You build a bigger telescope. That's the actual answer, not philosophy. Instruments. James Webb was built partly to test this exact tension by measuring those same variable stars and supernovae with sharper eyes than ever before. Early results haven't closed the gap. If anything, they've confirmed it's real. The discrepancy survived a $5 billion telescope. Some physicists now think we need new physics entirely, a form of dark energy that changes over time instead of staying constant. Others suspect our own galaxy sits in an unusually empty region of space, which would throw off local measurements without meaning anything is wrong with the universe itself. Neither idea is confirmed, neither is dismissed. That is what a live scientific argument actually looks like from the inside, not a settled fact waiting to be repeated on a poster. A number with a footnote the size of a crater. Maybe the true size of everything is 93 billion light-years. Maybe it's larger, curved, stranger than that. We are measuring a shadow and inferring the shape that casts it. That's not a failure of the science. It's the shape science takes at its edge, honest about the gap between what it can prove and what it suspects.